So thank you very much, everybody, for coming back after a very swift coffee break. You know, we like to keep you on your toes here. So our next speaker would have loved to have been here in person, but unfortunately has to join us virtually. But I'm really pleased, Thelma, that you have got up so early in the morning to join us in Venice. It's wonderful to see you again. So Thelma Krug is a former senior researcher at the Earth Observation Coordination at the National Institute for Space Research in Brazil under the Ministry of Science. She was elected vice chair of the Intergovernmental Panel on Climate Change for the sixth cycle of the panel for 2015 to 2023, after having been co-chair of the IPCC Task Force on National Greenhouse Gas Inventories from 2002 to 2015. And she's chair of the Terrestrial Observation Panel for Climate under the Global Climate Observation System. And she holds a PhD on spatial statistics from the University of Sheffield in the UK. Great seal of approval from me there. And she's been Deputy National Secretary at the Secretary on Policy and Programmes of Science at the National Secretary on Climate Change and Environmental Quality from the Ministry of Environment and Director of the Department of Policies to Combat Deforestation under the Secretary of Climate Change and Forests. So she has a huge, long list of accolades and many things, important things that she has done. And Thelma is going to talk to us to give us some perspectives on climate change. What are the possible futures and what can be done? So Thelma, I'm going to hand over to you and good luck.
Thank you. Okay, good morning to everyone from Brazil. It's cold today. As has been said, it's early hours here. But I am usually an early bird, so it is fine. Unfortunately, I could not be there in person. I would love to be in Venice, obviously. But unfortunately, my health didn't allow me to do that at this stage. So let me first thank the organizers of CO2 GeoNet for having invited me to be here and to provide some of the IPCC scientific findings during this sixth cycle. But before I do that, let me try to share my screen and hopefully we'll succeed. And I hope you can see the screen now. The title of my talk today will hopefully make me focus more specifically on what we can expect from possible future climates, their impacts, and what can be done. Hopefully, the presentation will show that we should try to avoid some of these futures and, honest pursue others that would, as the Paris Agreement has been trying to pursue, a level of warming that would limit also the impacts or risks of future impacts. So before I start, I thought it would be opportune for me to talk a little bit on the IPCC, because I am not sure if the audience as a whole has a sense of how all the scientific findings are constructed or developed through time. So if I go to my next slide, and I'm going to be very brief on this. So this talks about the role of the Intergovernmental Panel on Climate Change. Their own name already says that it's a governmental organization, and it's made up of member governments to the United Nations and also the World Meteorological Organization. And presently, the IPCC counts with 195 member governments. So hundreds of people around the world voluntarily contribute their time to the work of the IPCC as authors, review editors, and their role is to evaluate thousands of scientific articles that are published every year, and so as to provide an exhaustive synthesis of what is known about the drivers of climate change, its impacts and future risks, and how adaptation and mitigation can reduce these. So want to be clear that the IPCC does not conduct its own research, and in the selection of the authors that will be engaged in the development of the reports, It seeks to ensure geographical balance as well as gender balance. This is a little bit more complicated, but we are improving in this cycle. I guess on average we had 32% of women as authors, which has been a huge improvement from the previous cycle. And this is all meant to avoid any bias in the evaluation of the literature available. So the reports of the IPCC, they are neutral in relation to policies. But as we used to say, the report should be relevant, but should not be prescriptive. So some people ask, well, why doesn't the IPCC says that governments or people should do this or that? No, it's just tells what the science is saying, and the actions that follow that knowledge is up to those that can make the policies or can contribute in a way or another. So I'm gonna go fast on this as well, putting all these slides now. So the sixth cycle of the IPCC, as has already been said, it started in 2015 and it will end in 2023. The pandemic pushed us a little bit back on time, unfortunately. So this cycle has been a little bit longer. It's usually 6 years. So in 2023, we are going to have new elections that we will elect the members of the Bureau, 36 members altogether. So the chair, the vice chairs, the co-chairs of the working groups, as we are going to, I'm not going to go into that in details. So, so the IPCC, in terms of its structure, we have basically these three working groups that have been more engaged into in the production of the sixth assessment report, right? So this slide shows this structure. The arrows are pointing to the three working groups, which focus on different aspects of climate change. For instance, working group 1 works on the physical science basis of climate change, all the modeling approaches and so on. Working group 2 focuses on the impacts, adaptation and vulnerability. And finally, working group 3, I think, is the one that is more in the solutions space, as I like to say, working with the mitigation of climate change. I like always to say, mitigation, some people, I like to provide sometimes the definitions that IPCC gives to these things, and mitigation is sometimes not understood, which is the sources and enhance the sinks of greenhouse gases. So this is what we call mitigation, and so has this both things like enhancing the removals and reducing the sources of emissions. Okay, so together the reports from these three working groups, which we call contributions of the three working groups to the sixth assessment cycle of the IPCC, sums up to more than 5 years of work, comprise more, I think that in this cycle it's going to be much more than 7,000 pages, which makes of the IPCC the internationally recognized authority on the issue of climate change. So, in addition to these reports, the contributions of the three working groups, this cycle also produced 3 special reports that were delivered between 2018 and 2019. The first one that was, sorry, I'm going to this one. Yeah. So the first one, which was on global warming of 1.5 degrees Celsius. This one, it is very unlikely that this happens, but this one was an invitation from the Climate Change Convention that IPCC produces a report on the impacts of global warming of 1.5 degrees Celsius, and also the pathways that would lead to limiting the warming to that level. The second report was on climate change and land, where we talk about desertification, we talk about food security, so a lot of issues related to how climate change can affect land as a whole. And finally, we could not leave behind a special report on ocean and cryosphere in a changing climate. So all these reports make of this cycle one of the most ambitious ones, providing a wealth of scientific information where each finding is grounded in an evaluation of the underlying evidence and also agreement among the publications. And this is why you will find in the IPCC reports a calibration language, as we used to say, that reflects this evaluation that ranges, for instance, from virtually certain, that has a probability between 99 to 100% of an event happening, to exceptionally unlikely, where this probability would be basically between 0 and 1. So obviously you have, language in between, but this gives a sense of the maturity of that finding. And this is very helpful to governments when we say that it's usually certain that an event will occur linked to a finding. That gives a confidence to the governments and the public in general that that's something to be trustworthy. But interestingly enough, at every new cycle, what we see is like an evolution of this language, because you have more scientific literature to assess, and then you can, most of the time come to more evidence, as also the methods, models become more robust. So, with this brief introduction and background, I will now focus on the theme of my presentation, and would like to start by observations around the world that are calling everyone's attention and also concern. We have been seeing this year around the world an exceptional occurrence of extreme events. I will just list some. So China, for instance, was affected by one of the most severe hot waves registered until today due to its duration and intensity. Last May, also in Pakistan, the temperature reached 49.5 degrees Celsius in the city of Navabasht. And India experienced the hottest April in 122 years, with a maximum temperature of 49 degrees Celsius. And obviously the droughts and hot waves in Portugal, in Spain, parts of France, why not to say in Brazil, have also triggered large-scale fires. So I say that there is a question behind this that would go, could these events be attributed to climate change? Or are they part of natural climate variability, since these events used to happen? So what can science tell us about this? Well, science is clear that many climatic and meteorological extremes, such as hot temperatures, including the hot waves, strong precipitation, droughts, and tropical cyclones, can now be attributed to human influence, and that some of the hot extremes observed in the last decade would be extremely unlikely without this influence in the climate system. So in the case of hot streams, there is high confidence that the main driver is human-induced climate change. For strong precipitation, droughts, the signal is not so clear. So you can still find in some regions this digital of the human influence, but it's not as clear as for the hot streams. So, Working Group 1 report concludes that it's unequivocal that human influence has warmed the atmosphere, has warmed the ocean and the land, and that widespread and rapid changes in these components and other components of the climate systems have occurred. So the scale of recent changes across the climate system as a whole, atmosphere, ocean, land, and the present state of many aspects of the climate system are unprecedented over many centuries to many thousands of years. So I'm going to give some examples. And the first one is really scary to me, and I'll come back to it other times during my presentation. So, for instance, in 2019, with high confidence, the atmospheric concentration of carbon dioxide was higher than at any time in at least 2 million years. Concentrations of methane and nitrous oxide were higher than at any time in at least 800,000 years with very high confidence. And the global mean sea level has risen faster since 1900 than over any preceding century in at least the last 3,000 years. And in the last decade, I would say, the annual average Arctic sea ice area reached its lowest level since at least 1850. And the late summer Arctic sea ice area is smaller than at any time in at least the past 1,000 years. So the global nature of glacier retreat, with almost all of the world's glaciers retreating synchronously since 1950, is unprecedented in at least the last 2,000 years. So this is really, I'm going to show a slide that I think will make some of these points very clear, because it's interesting, because there are some people that still says, well, but we did have, all this warming in the past, sea level rise was even more than we can see now, but this has happened, and it took millions of years for that to happen. And what we are seeing now, and it is scaring the scientists, is the velocity, is the speed on which these events are now happening. These changes in the climate system are happening, especially since 1950. So I think this slide shows it very clear. So, but in addition to these findings that I mentioned, the report also points out that the temperatures during the last decade exceeded those of the most recent hot period around 6,500 years ago. And before this, the next hot period was around 125,000 years ago. So this can be seen from the panel on the left. This panel shows changes in the global surface temperature. It has been, part of it has been reconstructed from paleoclimate archives, and are shown in the solid gray line from year 1 to year 2000. And also from direct observations that you see in the solid black line from 1850 to 2020, and both relative to what we call the pre-industrial period between 1850 to 1900. So we can see this, exactly what I said, this huge jump, recent change that is observed. And what you see before that has been reconstructed. So the panel on the right, it shows in the black line the changes in the global surface temperature over the past 170 years, also relative to the pre-industrial time. And this is compared to climate model simulations of the temperature response to both human and natural drivers. So what you see in black are the observed temperature, global temperature on average, And what you see in brown is just a simulation including both human and natural factors. But so these natural drivers would be just like solar and volcanic activity that you see in green. And you see that if we only consider these natural factors, it absolutely cannot fit the observations that you see in black. Only when you have a simulation including the human and the natural factors or drivers, you can especially since 1950, as I said, you can have a better fit. So far I have concentrated on observed changes in the climate system. So that those observations come from multiple independent sources. You're talking about ice cores, you're talking about satellite data, you're talking about the paleoclimate archives, and also the meteorological ways of getting the information from all over the world, right? So, as I said, I concentrated so far on the observations and also the human contribution to the increase in the global surface temperature that today is about 1.1 degrees Celsius above pre-industrial times. This may seem to be small, but I'm going to show some slides afterwards and you're going to see that this can be quite impacting. So we know from science also that we have an almost direct relationship between the greenhouse gas emissions, the concentration of these gases in the atmosphere, and the increase in the global temperature. So we have, these linkages. And as I already mentioned in 2019, the emissions of greenhouse gases were the highest in 2 million years. So this means that if the problem is the emissions of greenhouse gases, the situation appears to be getting worse. And how worse it can become. So to address this question is a bit more complex, right? Because we have no observations or data to support conclusions and findings as I have been doing, even using the calibration language. So hence, the alternative is to develop scenarios on how the future can possibly evolve, and with this, seek to project the risks of impacts to all sectors of the economy and the society as a whole. So Working Group 1 evaluated the climate response to some illustrative emission scenarios that cover a set of possible future developments of the anthropogenic drivers of climate change that were found in the literature. So, this slide shows on the left 5 of these scenarios, right? And 2 of the last curves that you see from bottom to top, that you see in different colors of red, correspond to scenarios with high and very high greenhouse gas emissions. This goes up to the end of this century. So the 2 curves at the bottom that you see in different levels of blue are scenarios with low, very low emissions. And also there is an intermediate scenario that you can see in yellow. And also later on in this talk, I'm gonna talk, if you see the first 2 curves in blue, they go below the zero carbon dioxide emissions, right? But I'm gonna talk about that later on. And this does not happen with the other 3 scenarios. So in the panel on the right, we can see the warming contributions by scenario that are shown as change in the global surface temperature. And here I'm showing for the period 2081 to 2100, but IPCC provides these for different time spans. So this is all relative to the pre-industrial period. So we can see that for the very high emission scenarios, the last one, the best estimate of warming is going to be 4.4 degrees Celsius, and for the very low emission scenario, this is 1.4. So for each scenario, you can see these different bars, these 4 bars, that shows the projected increase in the temperature in the first one. So we are now, you can see the darker and the blue there, it's where we are now, 1.1. And then expected at the end of the century to reach 1.54. Obviously, there is a range. I'm not going to go into those details. It's just, to show more or less. Obviously, this is not like, even the 1.1, you have a range that goes to be less or more. So the second one of these bars is the contribution of carbon dioxide to this increase. And obviously, we can see for all of them that CO2 is the gas that most contributes to the increase. Then in the third bar, we have the contribution of non-CO2 gases. And finally, the last one is the contribution of some aerosols from land use. And that you see that they go below the 0, which means that they can bring some cooling to the warming. So the difference between these scenarios, as we can see, is very significant. And science shows us that the changes in the climate system become increasingly larger with increased global warming. So this includes increases in the frequency and intensity of hot streams, and hot spells as well, strong precipitation, droughts in some regions, and also the proportion of intense tropical cyclones. So with every increase in global warming, changes in these streams will continue to become larger. And the IPCC concludes that there will be an increasing occurrence of some extreme events unprecedented in the observational record with additional global warming, even at 1.5 degrees Celsius of global warming. So this slide shows on this panel A on the top a comparison between observed and simulated annual mean surface temperature change. The left map on the top shows the observed changes in annual mean surface temperature in the period of pre-industrial up to 2020 per degree Celsius of global warming. In the one on the right, a map that is based on model simulations that don't differ much at 1 degree Celsius of global warming. And the panel that goes below shows the simulated annual mean temperature change at different levels of global warming. And here we are presenting at 1.5, 2, and 4 degrees Celsius. So note that the changes do not occur uniformly around the globe. And the area more at the north of the northern hemisphere is the most affected, where we have the Arctic. And so with increases there in some periods of some seasons of the year being 2 to 2.5 times larger than the global average. And this is why I said previously that the 1.1 might seem to be small, but it's not distributed evenly. In some areas are more affected than others. But this is really striking to see the differences at, increasing from 1 degree Celsius to 1.5, 2, and 4 degrees, which is which is very striking to see these simulations. And when I talk about simulations, you can say, well, they're simulating. But when we look at what is observed and what is simulated on the top panel, we see that there is a very good coincidence about those. And this next slide shows the percent precipitation change also at the same levels of warming, 1.5, 2, and 4 degrees. There is less confidence, as I already mentioned, on precipitation and droughts, but I also show here the soil humidity loss or gain in terms of 4 degrees Celsius of warming. And what is striking, since I am here in Brazil, is what could be then been affecting the Amazon basin. Okay. So this next slide shows the projected changes in the intensity and frequency of hot temperature extremes over land. In the report, we can also find the same comparison for extreme precipitation on land and droughts in drying regions. But here I'm only showing for hot temperature extremes over land. So the projected changes, they are shown at global warming of 1 degree Celsius, 1.5, 2, and 4, relative to pre-industrial levels, and representing a climate without human influence. So the figures show frequencies and increases in intensity of 10 or 50-year extremes. The one on the left, 10-year extremes, to the right, 50-year extreme events from the base year, that's 1850 to 1900, under different global warming levels. So hot temperature extremes are defined as the daily maximum temperatures over land that exceeded on average once in a decade or once in 50 years during the 1850-1900 reference period. So it shows that hot temperature extremes that occurred once every 10 years in a world without human influence is projected to be 2.8 times more frequent at the present 1.1 degrees Celsius and more intense at 1.2 degrees Celsius. Whereas events that occurred once every 50 years are projected to increase their frequency 39 times at 4 degrees Celsius of global warming. So these projections give an idea of how the world will potentially be at different levels of warming, understanding that at the present level, human-induced climate change, including more frequent and intense extreme events, these have already caused widespread adverse impacts and related losses and damages to nature and people, and that is beyond natural climate variability. So widespread pervasive impacts to ecosystems, people, settlements, and infrastructure have resulted from observed increases in climate and weather extremes, including hot extremes on land and in the ocean, heavy precipitation events, droughts, and fire weather. So increasingly irreversible losses in terrestrial, freshwater, and coastal and open ocean marine ecosystems have been caused by climate change. Some losses are already irreversible, such as the first species extinction driven by climate change. Other impacts are approaching irreversibility, such as the impacts of hydrological changes resulting from the retreat of glaciers, or the changes in some mountain and Arctic ecosystems driven by permafrost thaw. So global warming reaching 1.5 degrees Celsius in the near term would cause unavoidable increases in multiple climate hazards and present multiple risks to ecosystems and humans. So the level of risk will depend on concurrent near-term trends in vulnerability, exposure, level of socio-economic development, and adaptation. So near-term actions that limit global warming to close to 1.5 degrees Celsius would substantially reduce projected losses and damages related to climate change in human systems and ecosystems compared to higher warming levels. But it cannot eliminate them all, as already mentioned. So this next slide now, it is coming from our working group 2, and it presents the 5 reasons for concern. RFC that you see there. It's a framework that IPCC has adopted since its 3rd assessment report. And the intention is to communicate the scientific understanding about accrual of risk for these broad categories that assume low to no adaptation. So the first reason of concern, and I'm going to focus only on the first 2 of them, refers to unique and threatened systems, such as coral reefs, the Arctic, and biodiversity hotspots. In the white color, you see that there is no associated impacts where detectable and attributable that could be detectable or attributed to climate change. In yellow, we show a moderate risk and indicates associated impacts that are both detectable and attributable to climate change with at least medium confidence. And the high risk shown in red indicates severe and widespread impacts, and in purple indicates the very high risk of severe impacts and also the presence of significant irreversibility or the persistence of climate-related hazards, combined with limited ability to adapt due to the nature of the hazards or impacts or risks. So the horizontal line that you see on the left that then denotes the present global warming of 1.1 degrees Celsius, which is used to separate the observed past impacts below the line from the future projected risks above it. So on the left, you are going to see the 5 illustrative emission scenarios that I have shown previously. And wherefore the intermediate high and very high emission scenarios, you can see that they are very much associated with the red or purple colors. For the present level of warming, some unique and threatened systems are transitioning to high risk with very high confidence level. The second reason of concern refers to extreme weather events where can one observe a high risk of impacts for even below 2 degrees Celsius. In the 3rd assessment report, the IPCC focused only on these reasons for concern, but it has expanded these hugely to include impacts, even regional ones that are not shown here, despite the title showing global and regional risks. These are global. And these are provide a good visual reference to where we could be leading with these 5 scenarios of how the future could develop. So this slide shows the risk of extinction in biodiversity hotspots that could increase by about tenfold as warming rises from 1.5 to 3 degrees Celsius. So species extinction and losses of entire ecosystems, such as mountaintops, tropical coral reefs, coastal wetlands are projected to be lost, even if we temporarily exceed 1.5 degrees Celsius warming for several decades. We are going to talk about overshoot scenarios later on in this presentation. And this is why I'm talking about temporarily exceeds. So one of the conclusions of the working group to report is that if global warming transiently exceeds 1.5 degrees Celsius in the coming decades or later, and that's the overshoot I'm going to talk later, then with high confidence, many human and natural systems will face additional severe risks compared to remaining below 1.5 degrees Celsius. So depending on the magnitude and duration of the overshoot, this exceedance, in this case 1.5, some impacts will cause the release of additional greenhouse gases, and some will be reversible, even if global warming is reduced. Let's go to the next slide, and this slide sums up the projected future global risks, and I highlight that regions that are highly dependent on snowmelt could experience a 20% decline in water availability for agriculture beyond 2050, being one of the potential drivers of migration. Adaptation to water-related risks and impacts make up the majority of all documented adaptation. The report says that irrigation is an effective way in reducing drought risk and climate impacts in many regions, and have many livelihoods benefits, but needs appropriate management to avoid potential adverse outcomes, which can include accelerated depletion of groundwater and other water sources and increased soil salinization. So many adaptation options exist and are used to help manage projected climate change impacts, but their implementation depends on the capacity and effectiveness of governance and decision-making processes. However, adaptation progress is unevenly distributed with observation adaptation gaps, which is the difference between actual implementation adaptation and a socially accepted goal. So many initiatives prioritize immediate and near-term climate risk reduction, which reduces the opportunity for transformation adaptation. So I have so far outlined the challenges we face and how these will increase in many places, but progress is uneven, as I already said, and we are not adapting fast enough. But adaptation, I'm sorry. Adaptation is just one part of the response to climate change, and reports from all working groups are very clear that unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting global warming to 1.5 degrees Celsius will be beyond reach. However, I'm sorry. As I previously mentioned, the emissions of greenhouse gas in 2019 were the largest in human history, and the anthropogenic emissions have continued to rise across all major groups of greenhouse gases. And you can see in this slide, CO2 from fossil fuels this is in global net anthropogenic greenhouse gas emissions, and this is in billions of tons. And this goes from 1990 to 2019. It's very clear that the largest contribution comes from CO2 from fossil fuel and industry. So you can see methane over there with 18%, net CO2 also coming from land use, agriculture and forestry. From forestry is basically deforestation, but this gives us an idea. And on the top, you see that in 2010, the emissions were 53 billion tons. They jumped to 59 in 2019, just basically 12% increase. And you can see the evolution of these gases. And I thought it would also be interesting because this provides some additional details, showing this panel on the top, the annual anthropogenic greenhouse emissions by major economic sectors, energy, industry, agriculture, and so on. And in panel B, There are underlying trends by region. So some of you want to look a little bit on this. So in 2019, approximately 34 of the total anthropogenic greenhouse gas emissions came from the energy supply sector, 24 from industry, 22 from agriculture, forestry and other land use. Yes, from forest and land use, it would be between 10 and 12%, 50% from transport, and 6% from buildings. So the greenhouse gas trends over 1990 to 2019, it varies, as you can see below, widely across regions and over time, and also across different stages of development. In 2019, around 41 of the global population live in countries emitting less than 3 tons of CO2 equivalent per capita, with a substantial share of this population lacking access to modern energy services. Most of the emissions from the developing world, after Africa, Latin America, and parts of Asia, are related to land-based activities, mostly related to agriculture. You can see those blue bars, basically in in Latin America very clearly, South Asia, Southeast Asia, Africa, whereas in Europe, North America, you don't see that as much. So it is very clear that we are not on track to limit warming to 1.5 degrees Celsius. This slide shows in the red curve the trend of emissions in billion tons until 2050 if we maintain the current implemented policies, and where we need to be, which would be the blue line, to limit warming to 1.5 degrees Celsius with no or limited overshoot. So just anticipating temperature overshoot is defined by the IPCC as the temporary exceedance of a specified level of global warming. When we say temporary exceedance, it would go beyond 1.5. When we say limited, we mean 0.1 degrees Celsius above 1.5. Higher overshoot would be higher than that. And then it would come back to 1.5 by the end of the century. This is why it's temporary. So on the right of the slide, we see the cuts in greenhouse gas emissions for limiting warming to 1.5 degrees Celsius, and which is 43% for 1.5, 27% for 2 degrees Celsius until 2030, with the peak in emissions occurring for both by 2025. So this slide from the special report of 1.5 degrees Celsius, it presents the assessed emission pathways that limit global warming to 1.5 by the end of the century. So it shows that there are different ways to get there. So the envelope that you see of these pathways includes some with no or limited overshoot, which are within the envelope of blue, and others with higher overshoot, which are depicted here in gray. But regardless of the pathway assessed by the IPCC, all have in common that CO2 emissions are reduced to net zero globally around 2050 for 1.5 degrees Celsius and around 2070 for 2 degrees Celsius. So for 1.5, this reduction implies deep cuts in CO2 emissions from energy supply and demand, around 74%, agriculture, forestry, and other land use, around 13%, and additional 13% cuts in non-CO2 emissions from land use, energy, and industry. So now we go from working group 3, which based on a detailed sectoral assessment of mitigation options, the report estimates that mitigation options costing $100 or less per ton of CO2 equivalent could reduce global greenhouse gas emissions by at least half of the 2019 level by 2030. And this is really impressive. So large contributions with costs less than $20 per ton of CO2 equivalent come from solar and wind energy efficiency improvements, reduced conversion of natural ecosystems, and methane emission reductions from coal mining, oil and gas, and also waste. The report provides mitigation opportunities and options for all sectors, but also indicates the barriers that exist for their implementation: institutional barriers, technological barriers, financial barriers, social cultural barriers, and geophysical barriers, and so on. Right. So, for instance, and I only picked up the energy one. For instance, for energy, reducing greenhouse emissions across the full energy sector requires major transitions, including a substantial reduction in overall fossil fuel use, the deployment of low emission energy sources, switching to alternative energy carriers, and energy efficiency and conservation. So net zero CO2 energy systems entail a substantial reduction in overall fossil fuel use, minimal use of unabated fossil fuels, and use of CCS in the remaining fossil system. Also, electricity systems that emit no net CO2, widespread electrification of the energy system, including end users, energy carriers, such as sustainable biofuels, low emissions hydrogen, among several others. So, in addition to deep, rapid, and sustained emission reductions, carbon dioxide removal methods can be implemented to counterbalance residual, hard to abate emissions, including from the energy sector, and also to achieve the net negative CO2 or greenhouse gas emissions in the long term, if deployed at level exceeding annual residual emissions. So the Working Group 3 report indicates that the deployment of carbon dioxide removals, the CDR, is unavoidable if net zero CO2 or greenhouse gas emissions are to be achieved. IPCC refers to CDR as anthropogenic activities that remove CO2 from the atmosphere and store it durably in geological, terrestrial, or oceanic reservoirs, or also in products. And although many CDR methods exist, they vary in terms of their maturity, removal process, time scale of carbon storage, mitigation potential, cost, co-benefits, impacts and risks, and also governance requirements. Also, depending on the CDR method, the site-specific context and the scale, there can be risks and co-benefits of its deployment to ecosystems, biodiversity, and people. So CDR methods have a range of side effects that can either weaken or strengthen the carbon sequestration and cooling potential of these methods and affect the achievement of sustainable development. So changes in surface albedo, water cycle, marine ecosystems productivity can be some of the side effects. On land, CDR can affect water quality and quantity, food production and biodiversity, with the largest benefits being obtained with methods that seek to restore natural ecosystems or improve soil carbon sequestration. I'm coming almost to an end. So a final note on CDR. It's known that during the industrial era, the CO2 emitted by combustion of fossil fuels and land use change has been redistributed between the atmosphere, the land, and ocean carbon reservoirs due to carbon cycle processes. Over the last decade, from 2010 and 2019, 46% of the emitted CO2 remained in the atmosphere. 23% was taken up by the ocean, and 31% by the terrestrial biosphere. So when CDR is applied during period in which human activities are net CO2 sources to the atmosphere, and the amount of CO2 removed by the CDR is smaller than the net source, CDR acts to reduce the net emissions, and the land and ocean sinks continue to remove CO2 emissions from the atmosphere, as is the case historically. However, when CDR removes more CO2 emissions than human activities emit, and atmospheric CO2 declines, then the land and ocean sinks initially continue to take up CO2 from the atmosphere, but after some time, depending on the magnitude of the removal and the rate and amount of CO2 emissions prior to the CDR application, the land and ocean carbon reservoirs begin to release CO2 to the atmosphere, making CDR less effective. So this explains one of the gaps that has been identified by Working Group 1, which is to improve understanding of the effectiveness of CDR methods to lower atmospheric CO2 and reduce warming, taking into account these Earth system feedbacks. So, with this, I come up to the end of my presentation. I hope, obviously, this is just a very small summary of all the scientific contents of the IPCC in the 3 reports. But I really tried to bring, elements from each one of them, in particular to address the theme of my presentation, which is just, how can future climate be and what can be done? So it's very clear that we can go from a world that is much more sustainable than other worlds that are much less sustainable, and we are going to see, much more risks to natural and human systems. So thank you very much for your attention. And the final slide, the evidence is very clear. The time to act is now. And I thank you very much for your attention. And I hope I didn't go too much beyond my time.